Welcome to the video on user datagram protocol, that is UDP. At the TCP/IP protocol suite, it specifies two protocols for the transport layer, UDP and TCP. We first focus on UDP and the simpler of the two, and before discussing the TCP. So in figure 11.1, it shows the relationship of UDP to the other protocols and layers of the TCP/IP protocol suite. UDP, if you see, it lies between the application layer and the IP layer, and like TCP serves as the intermediary between the application layer and the network operations. Transport layer protocol usually has several responsibilities. One is to create a process-to-process communication, and UDP uses port numbers to accomplish this. Another responsibility is to provide control mechanism at the transport layer. UDP does this task at a very minimal level. That is, there is no flow control mechanism and there is no acknowledgement for received packets. UDP, however, does provide error control to some extent. So we'll see that. If UDP detects an error in the received packet, it silently drops it. Right. So this is how it is going to happen, and it's going to generate the ICMP for that. UDP, understand, is called a connectionless unreliable transport protocol. It does not add anything to the services of IP except for providing process-to-process communication instead of host-to-host communication. So process-to-process means it goes to the actual process. Also, it performs very limited error checking. Question is, if UDP is so powerless, why should a process wants to use it? With the disadvantages comes some advantage. UDP is a very simple protocol using a minimum of overhead. If a process wants to send a small message and does not care much about the reliability, it can send UDP. It can use UDP. Sending a small message using UDP takes much less interactions between the sender and the receiver than using TCP. Right. So this is how the UDP is going to be there. And before we go into the details of the other things, let us look at it one by one. So process-to-process communication. So before we examine UDP, we must first understand how host-to-host communication and process-to-process communication and the differences between them. Right. So the IP is responsible for communication at the computer level. That is host-to-host communication. As a network layer protocol, IP can deliver the message only to the destination computer. However, this is an incomplete delivery. Right, the message still needs to be handed to the correct process. So this is where the transport layer protocol, such as UDP, takes over. So UDP is responsible for delivery of the message to the appropriate process. So if you look into this figure, it is like to the appropriate process. That is, it shows the domains of the IP and the UDP. So to go into the details of this, IP protocol, if you see, we have just discussed that it is host to host, and then UDP protocol, with the help of port numbers, it will be process to process. So what is this port number all about? Although there are a few ways to achieve process-to-process communication, the most common one is through the client-server paradigm. So the process on the local host, called a client, needs services from a process usually on the remote host, called a server. So both processes have the same name, the client and server. For example, they get the day to get the day and time from a remote machine. We need a daytime client process running on a local host and a daytime server process running on a remote machine. However, operating systems today support both multi-user and multi-programming environment. A remote computer can run several server programs at the same time, just as the several local computers can run one or more client programs at the same time, right? So for communication, we must define the local host, local process, remote host, and remote process. So now the local host and the remote host are defined using IP addresses. To define the processes, we need a second identifier called port numbers, right? So in the TCP/IP protocol suite, the port numbers are integers between 0 to 65535. So like the client process defines itself with the port number chosen randomly by the UDP software running on the client host, and this is known as ephemeral port number. So there are various port numbers like uh, ephemeral port numbers, then well-known port numbers, and the port numbers available for private use, right? So well-known port numbers are between 0 to 1023. So all the well-known services would be within this port numbers, right? We'll use these port numbers, right? And the registered ports are like the ports ranging from 1024 to 49151. These are not assigned, or these are not assigned, and maybe you can say that they are controlled by IANA, right? Internet Addressing Numbering Authority. They can only be registered with IANA to prevent the duplication. And the dynamic ports, the ports ranging from 49152 to 65535 are neither controlled nor registered. They can be used by any process, right? So these are the ephemeral port numbers. So no, there are various applications, well-known ports, no, they are used, like let's say ECO is 7. Then more importantly, if you see this SNMP, SMTP, and so on. So there are various port numbers which are already reserved for special type of purposes, and they are well-known port numbers, right? So coming back to this, no, the IP addresses versus port numbers. So what will happen is, no, the IP when the packet is coming, to the host. So IP will identify that, okay, this is the host which has been identifying this packet, and then this packet, after dropping the headers, will reach to the top layers, the transport layer, where it will identify that this is the port number 13, and then based upon that, that packet will be provided to the appropriate process, right? So in this way, things would be there. And before we go into the details of the other things, we should understand what is the socket, right? So as we have seen, UDP needs two identifiers, the IP address and the port number at each end to make the connection. So we need this IP address and the port numbers. The communication of an IP address and a port number is called a socket address. The client socket address defines the client process uniquely, just as the server socket address defines the server process uniquely. So to use the services of UDP, we need a pair of socket addresses, the client socket address and the server socket address. So these these 4 pieces of information are part of the IP header and the UDP header. So the IP header contains the IP address, and the UDP header contains the port number. The IP header contains the IP address, and UDP header contains the port number. Right. So now, considering that we now have the port numbers for the process identification and the IP address for the host identification, we now have to create the user datagram, right? So UDP packets basically are called the user datagram, right? And have the fixed size header of 8 bytes. So this next figure will show you what is the format of the user datagram. So we'll see that. This is the user datagram format, and the fields are as follows. So if you see the header, it is of 8 bytes, and the fields are source port number, destination port number, length of the header, the UDP header, and the checksum. So let us see it one by one. The source port number. This is the port number used by the process running on the source host, and it is 16-bit long. So which means that the port number can range from 0 to 65535. If the source host is the client, the port number in most cases is an ephemeral port number requested by the process and chosen by the UDP software running on the source host. And if the source host is the server, the port number in most cases will be a well-known port number. Right? Likewise, the destination port number will be there in similar lines. And we come to the length part. Then this is a 16-bit field that defines the total length of the user datagram, header plus data. So this the 16-bit field can define the total length of what? That 2 to the power 16, that is 0 to 65535 bytes. However, the minimum length is 8 bytes, which indicates a user datagram with only header and no data. So therefore, the length of the data can be between 0 to 65507. That is 65535 minus 20 minus 8 bytes, which is nothing but 20 bytes for the IP header and 8 bytes for the UDP header. So the total length, the length field in the UDP user datagram is actually not necessary. The user datagram is encapsulated in the IP datagram. So there is a field in the IP datagram that defines the total length. So there is another field in the IP datagram that defines the length of the header. So if we subtract the value of the second field from the first, we can deduce the length of the UDP datagram that is encapsulated in an IP datagram. So UDP length is equal to IP length minus IP header length. So however, the designers of the UDP protocol felt that it was more efficient for the destination UDP to calculate the length of the data from the information provided in the UDP user datagram, rather than asking the IP software to supply this information. So we should remember that when the IP software delivered the UDP user datagram to the UDP layer, it is already dropped. It has already dropped the IP header, right? So that's why this information is going to help with what is the total information present in the UDP, right? And next is the checksum. This field is used to detect errors over entire user datagram. And the checksum is discussed in the next section, and we have already seen what is checksum in the the flow control and error control part of the data link layer, right? So UDP checksum calculation is different from the one for IP and ICMP. Here, the checksum includes 3 sections: the pseudo header, the UDP header, and the data coming from the application layer. Right. So this is how the pseudo header for the checksum calculation is there, along with the header and along with that there is some data. Right. So checksum will be calculated in the way that we have already seen. So it will be 16 bits together and then separated by 16 bit and then addition and then summation of that, and then finally we do the complement, and then this value will be kept as part of the checksum bit. Right. So I'm not going to go into the details of the checksum part. Right. But yes, this is important. There is a pseudo header, there is a header of the UDP, and then the application layer data, right? So this is how the checksum is calculated. And then we are interested to see what is the UDP operation altogether, right? So UDP uses concept common to the transport layer. And these concepts will be discussed here briefly and then expanded in the next chapter of TCP, right? So one is connectionless service. What is connectionless service? We will see that what is connectionless service and what is flow and error control. So as mentioned previously, UDP provides a connectionless service. And this means that each user datagram sent by UDP is an independent datagram. So that means there is no relationship between the different user datagram, even if they are coming from the same source process and going to the same destination program. So the user datagrams are not numbered, and also there is no connection establishment and no connection termination as in the case of TCP. So this means that each user datagram can travel on a different path. And one of the ramifications of being connectionless is that the process that uses UDP cannot send a stream of data to UDP and expect UDP to chop them into different related user datagrams. Instead, Each request must be small enough to fit into one user datagram. That's why only those processes sending short messages should use UDP, right? So it is only be used for short messages. Next is flow and error control. So UDP is very simple, unreliable and unreliable transport protocol, and there is no flow control, and hence no window mechanism is required. The receiver may overflow with some incoming messages. There is no error control mechanism in UDP except for the checksum, right? So that we have seen. This means that the sender does not know if the message has been lost or duplicated. When the receiver detects an error through the checksum, the user datagram is silently discarded, right? So this is how the message is going to be discarded. And the lack of flow control and error control means that the process using UDP should provide for this mechanism. So it is not then the responsibility of the UDP protocol. The process which is providing this service has to make sure that the flow control and error control and the connections has to be made reliable somewhere. So UDP doesn't take care of it. Next is encapsulation and decapsulation. To send a message from one process to the another, the UDP protocol encapsulates and decapsulates messages. So what is encapsulation here is like when a process has to send a message through UDP, it passes the message to UDP along with the pair of socket addresses and the length of data. So, excuse me, UDP receives the data and adds the UDP header. What will happen is UDP then passes the user datagram to the IP with the socket addresses, right? And IP adds its own header using the value 17 in the protocol field, indicating that the data has came from the UDP protocol. So the IP datagram is then passed to the data link layer, and the data link layer receives the IP datagram, adds its own header and possibly a trailer, and passes it to the physical layer, right? So the physical layer encodes the bits into electrical or optical signals and sends it to the remote machine, right? So in similar way, in the opposite way, as such, the decapsulation will take place, and I think it is self-explanatory, so I will not discuss the things. And the diagram itself is saying you everything, right? So next is queuing, and we have talked about various ports without discussing the actual implementations of them. In UDP, queues are associated with ports. So understand, queues are associated with the ports, right? At the client side, when the process starts, it requests a port number from the operating system. And some implementation creates both the incoming and the outgoing queue associated with each process. Other implementations create only an incoming queue associated with each process. So there are different implementations which are possible. Note that even if the process wants to communicate with multiple processes, it obtains only one port number and eventually one outgoing and one incoming queue. So the queues opened by the client are in most cases identified by ephemeral port numbers, and the queues functions as long as the process is running. So once the process is down, these queues will be removed. When the process terminates, the queues are actually destroyed. That's what I mean to say, right? So the client process can send message to the outgoing queue by using the source port number specified in the request, and UDP removes the messages one by one, and after adding the UDP header delivers them to IP, right? And outgoing queue can overflow, and what will happen is, if this happens, the operating system can ask the client process to wait before sending any more messages, right? And when the message arrives to the client, what will happen is the UDP checks to see if the incoming queue has been created for the port number specified in the destination port number field of the user datagram. And if there is such a queue, the UDP sends the received user datagram to the end of the queue. It will be just be appended at the end, right? So if there is no such queue, right, then the UDP discards the user datagram and asks the ICMP protocol to send a port unreachable message to the server. So all the incoming messages for one particular client program, whether coming from the same or from the different server, are sent to the same queue. And incoming queue can overflow. Even an incoming queue can overflow. So if this happens, the UDP drops the user datagram, and what will happen is an ask for a port unreachable message to be sent to the server. Right. So at the server side, what could be the possibilities? The mechanism of creating queues is different. We will see in future chapters that there are different types of servers. However, in its simplest form, a server asks for incoming and outgoing queues using its well-known port numbers when it starts running. So the queues remains open as long as the server is running, right? So when the message arrives from the for a server, UDP checks to see if the incoming queue has been created for the port numbers specified in the destination port number field of the user datagram. If there is such a queue, UDP sends the received user datagram to the end of the queue. And if there is no such queue, UDP discards the user datagram and asks the ICMP protocol to send a port unreachable message to the client. So in this way, the things would be handled. The the outgoing queue can also overflow. If this happens, then the operating system asks the server to wait before sending any more messages. So in this way, like it is supposed to see that the queues are properly handled by the system. So if there is incoming queue, there is outgoing queue, and various applications will be making use of it. Next is multiplexing and demultiplexing. So once we look into all these things, now we'll combine all this stuff to the actual UDP process, right? So we call it as UDP package. Okay, what is multiplexing and demultiplexing? Here is in a host running a TCP/IP protocol suite, there is only one UDP, but possibly several processes that may want to use the services of UDP. So to handle this situation, UDP multiplexes and demultiplexes, right? So what is multiplexing here is at the sender side, there may be several processes that needs to send user datagram. However, there is only one UDP. So this is many to one relationship and requires multiplexing. UDP package accepts messages from different processes differentiated by their assigned port numbers. And after adding the header, UDP passes the user datagram to the IP, right? And on the demultiplexing side, at the receiver side, there is only one UDP. However, we may have many processes that can receive user datagrams. This is one-to-many relationship and requires demultiplexing. So UDP receives user datagrams from IP. After error checking and dropping of the headers, UDP delivers each message to the appropriate process based on the port numbers, right? So this is how it is going to be there. And then this is how the basic things that are required we have seen. And now we shall see what are the various uses of UDP. So UDP is suitable for, first is UDP is suitable for processes that require simple request response communication with little concern for flow and error control. This is not usually used for a process that needs to send lot of data, that is bulk data, such as FTP and so on. And UDP is suitable for a process with internal flow and error control mechanisms. For example, like TFTP, Trivial File Transfer Protocol. Processes includes flow and error control in itself, and it can easily use UDP. Right. So UDP is again is a suitable transport control for transport protocol for multicasting and broadcasting. So multicasting and broadcasting capabilities are embedded in the UDP software, but not in the TCP software. Right. So this is really interesting. And UDP is used for management process such as SNMP, Network Management Protocol. Right, and UDP is used for some route updating protocols such as routing information protocol, that is RIP. So in this section, till now we have seen the basics related to the UDP, various port numbers. We have seen the use of UDP, various usages of UDP, and the Next topic, which is going to combine everything, is the UDP package. So to show how UDP handles the sending and receiving of UDP packets, we present a simple version of the UDP package. So the UDP package involves 5 components: a control block table, then input queues, a control block module, an input module, and an output module. So we'll see it one by one, right? So control block table. So in the control block table in our package, UDP has control block table to keep track of the open ports, right? So whatever the ports are open, we can come to know from this control block table. So each entry in this table has a minimum of 4 fields. These fields are the state information, which we can through which we can come to know whether it is free or in use, and the other fields are the process ID, the port number, and the corresponding queue number, right? And so this is the information which is going to be present inside the control block table, right? And this control block table is going to be present in the UDP package, right? Next is input queues. So input queues, if you see, our UDP package uses a set of input queues and one for each process. So in this design, no, we do not use output queues. So there is no output queue present here. Control block module. Control block module is responsible for the management of the control block table. When a process starts, it asks for a port number from the operating system. The operating system assigns well-known port numbers to the servers and ephemeral port numbers to the client, and the process passes the process ID and the port numbers to the control block module, right? So to create an entry in the table for the process, the module does not create the queues. The module does not create the queues, and the field for queue number has the value of 0. Note that we have not included a strategy to deal with a table that is full. So that is left as an exercise to see in the things to follow. Next is input module. Input module receives a user datagram from the IP. It searches the control block table to find an entry having the same port number and as this user datagram. And if the entry is found, and the module uses the information in the query in the entry to enqueue the data. And if the entry is not found, it will generate the ICMP message. Right, and there is an output module also. So what is that output module? Output module is responsible for creating and sending user datagram. Right. So there are few examples which are there. I'm going to share this presentation to you on Google Classroom. I request you to go through this video multiple times and note down certain important points from that, and you can have the queries when we are meeting in the classroom. Thank you very much.